calculus, and today we'll be talking about conditions for local transformations between sets of quantum states. So go ahead, Ritabrata.
Yeah, so I just need to share my screen actually. So
Yes.
I think share my uh, okay. So let me just try to make it a full screen, and just a second. Just a second. Let me know whether you can see it or not.
Yeah, I'll tell you.
Okay, just 1 second. And can you see it?
Yeah, we can
Can
see
you see
your.
the full screen or not?
Yes, yes,
Full screen, right?
yes,
Okay, good.
yes.
Yeah, so thank you everyone, and thank you for, I should thank the organizers for calling me to give this lecture. And okay, so this work is joint work with Professor Shamsubra Bandyopadhyay and Sharanath Haldar, who is now in Warsaw. So let me tell exactly what is this transformations of the between the sets of quantum states. Um, so the at the end of this lecture, at least I want you to understand the problem, and I should also point out and what are the things has been done on this direction. And LOCC is the part on which we are the first one to look into it, but but yeah, there are, we have not completed the whole calculations, as you can see quickly. So this paper came, the first paper on this thing. We are also working on something more came in PRA last year, and let's see. So so the what is the state transformation problem? So let us say, so this is also in mathematics called as the as the problem of, you know, interpolation problem between sims. So let us have this system, that situation in which you have a set of input states, let's call it rho 1, rho 2, rho n, and you have a set of output states which are call it as, let's say, sigma 1, sigma 2, sigma n. And the scheme is the following: you want to find out a transformation which will take the rho I to sigma I. So rho 1 goes to sigma 1, rho 2 goes to sigma 2, and so on and so forth. Okay. So this is, if you recall, those who are in actually undergraduate and doing a course in mathematics, then probably may recall this thing, that this is something very similar to what you do in interpolation problems in mathematics, that you have a couple of points given inputs and a couple of points given as the outputs, and then you are asking a question that can you, can you approximate the function, can you find out the function which takes this set of input points to the output points? And practically, it's there are theorems on it, that it is that you can do it with respect to a trigonometry, is a polynomial function, and so on and so forth. But here we are doing quantum mechanics, so I can ask the question as that is that transformation can be done by using a quantum channel. Okay, so whether there exists a quantum channel phi such that phi of rho j is equal to sigma j for each j. So this problem was initially thought by, it's not actually an original problem in quantum theory itself. Like many things in quantum theory or the quantum information theory, the history actually comes from statistics. So the idea there is the following, that is there suppose you assume that there is a set of, probability distributions p1, p2, pn, and then there are another set of probability distributions q1, q2, qn. The question is that whether it is possible to have a kind of a stochastic map which transfers this pi to qi. Okay, You can ask the question, why it is so important? The idea is that, this is something exactly what you want to do for the multiple hypothesis testing. And I'll come to this point after telling the quantum version of this. So quantum version first was considered by Alberti and Ullmann in 1980s as in this paper. And the question was much more simpler. That is, let's consider the qubit system. Of course, they didn't call it qubit. So they considered the two Hilbert spaces H and K. Both are of C2. And it had two input states, rho1 and sigma1, and two output states, rho1 and rho2, and two output states, sigma1 and sigma2. And the theorem, which was the following, is that if I have such a map, which they called it as a stochastic map, which takes the rho1 to sigma1 and rho2 to sigma2, if such a map is possible, if and only if for each positive real number t, this inequality holds. This is a trace norm. This trace inequality actually holds. Okay. Now, let me come back to the original problem slightly for the classical statistics. So if you consider you have two probability distributions, P1 and P2, and two other probability distributions, sigma 1 and sigma 2, and you ask the classical system that is there a stochastic map which takes from P1 to P1 to Q1? Let's say, okay, so P1 to Q1 and P2 to Q2. What is the kind of, why you need to look for this kind of things? Well, this is exactly the thing what we do in the hypothesis testing for the classical probability. Okay, so whether to accept the hypothesis P1 or whether to accept the hypothesis as P2. Okay, these are the kind of things which we do, and the general version is what is called as the multiple hypothesis testing. Now, actually, Ullmann, now let's come back to the quantum side. So they also, Alberti and Ullmann also, both of them tried to figure out that whether it is possible to have a quantum version of this whole game. And they found out a necessary and sufficient condition for the case when you are considering qubits and when you have only two input and two outputs. But in the paper itself, they actually made a comment that if you increase the number, even for the qubits, or if you increase the dimension, then this thing is not so simple and they have no clue how to do that thing. In fact, later Ullmann came up with a much more general structure in which he showed that the fidelity of the, if you increase the number of inputs, rho1, rho2, rho-n, and in outputs as sigma 1, sigma 2, sigma n with the same condition that rho I goes to sigma I, then there is a fidelity inequality is possible if there is a transformation. So what we write is the S of rho is kind of the set of all rhos are transferred to the set of all sigmas. So this is, in this way, I call it as a set transformation problem, that you have a set of input states rho and you have a set of output states sigma. You want to find out a map which for all respect, we want to find out a quantum channel which is completely positive trace preserving map, as you all know. And if there is such a thing possible, then the fidelities of these pairs will have this nice inequality, which is actually, now it looks pretty easy. Now that after we are sitting in 2022, and it may seem quite easy, but it required quite a lot of work at that time. Okay. Now, it was still in 1985, but then, meanwhile, the quantum information theory came, quantum computation theory came, and people started looking at it. And Klefs and others actually worked it out then in 2000, and then Andreas Winter, Klefs, they also worked for the case of the qubit systems, and which was much more operationally significant. And you can check the papers which came up at that time. But there was actually a similar line of thoughts came by the mathematicians. So Chikun Lee and Sewa Kung actually worked on the same problem. And in the year 2011, this paper came in linear and multilinear algebra, which we generally write it as LAMA. So they actually looked a lot of restrictions on it. So first restriction, they thought the following thing, that let us say, okay, so let's have this rho i's and sigma i's, and let us assume that they are all simultaneously diagonalizable. By that, what does it mean? It means that you are actually looking for the diagonal matrices, all the rho i's are and all the sigma i's are diagonalized, and they are diagonal matrices, and there is only one unitary matrix which does the thing, does this job. So basically, you are considering a situation where the diagonals goes to the diagonals. And if that is the case, then what are the things possible? Can you write down the map explicitly? They came up with a nice set of conditions on that. But you understand that this is a very, very strong condition, because you are asking that all the rho i's will be diagonalized by a single unitary and all the sigma i's will be diagonalized by a single unitary. So, that doesn't give us something big insight on it, but that was a very small step but significant step. Then much more much more complicated thing came up by Davidson, Baynard, Ocelat, and one more person, I forgot the name, which the paper came in IMRN. They said that it is possible if and only if there is something called a joint numerical range of all the rows and the joint numerical range of all the sigmas, and if they are all same, in that case, there is a transformation is possible. But look, that transformation is possible by using an unital completely positive map. That's why I used a different signal phi here. It's not always the and you know that the unital completely positive map need not be a channel. So there is of course an issue in this matter to actually apply it directly. Of course, a person who is more mathematically minded may point out that if you have a CPTP map, its dual of the map is actually an unital, so you can use that thing. The problem is that if you try to do that, there is an algorithmic version of this paper also to construct at least one such object channel, but that does not work it out properly for the dual situation. So there is still a bit of gap into for operationally converting this whole thing in terms of the channels. Then almost around the same time, Gladgold and Francisco Bushmead and several other people actually were looking on the same problem from the thermodynamical principles. Okay, so what they did is somewhat, I can explain it in a short in 2-3 minutes. The point is the following. So you have the rho i's and sigma I. So you are putting in a tag kind of thing. So you take I tensor rho I is like bra I tensor rho I, and similar, and take the sum over all the things, normalize that object, and similarly you put that I summation of I into sigma I and normalize that thing. So basically it's a state, it's a classical quantum state, and it's a one classical quantum state, and you are trying to find out whether there is a single object, single completely positive trace preserving map such that one tensor, that map is actually sending this object to this classical quantum state to that classical quantum state, and then you take the measurement and you find out, you tell that that works out, and it this is the thing which they called it as a measurization, non-commutative measurization problem. They eventually found out that this is equivalent to several thermodynamical calculation of or estimation of several inequalities, thermodynamical inequalities. In particular, they are all involving the mean inequality of it. So I don't want to go in that direction too much, but all these things are equivalent, and eventually they can be written in terms of what is called as a semi-definite optimization problem. Okay. So now what did we do? So when we looked at this problem, we thought that let us ask this question for LOCC version. There are reasons, of course, as you see that the LOCC is operationally more strong. And in several cases, what happens is that this, the LOCC things works out, can be much more complicated that even for the cases in which the mathematical structure is well known. For instance, see, like the state distinguishability problem. So you know things about the state distinguishability. There are nice mathematical theorems for doing that thing. But then you ask the question that, okay, can you distinguish two sets by using the LOCC? And then you see that there are several difficult situations arise and people work on it still now. So we also ask that question that what happens for the LOCC of that whole thing. Okay. So formally speaking, I have a set of rows, row 1, row 2, row n, and I have a set of sigma, sigma to sigma n. So let us call that S row is the set of all those things, and sigma is the set of output sets. And whether it is possible to have an LOCC protocol, a single LOCC protocol, which can convert all the rows to all the sigmas. So row I goes to sigma I, but the protocol has to be the single protocol. Okay. Now it is LOCC, and this is the first time we looked at the whole thing. So what we thought was that, okay, let's make some assumption. So first of all, it has to be bipartite, otherwise you don't know why we should bother about the LOCC. So the input and output systems has to be the same. So that means your Hilbert space of both input and output, it has to be something like bipartite, H8 tensor HP. And second, if you consider, if you consider the states, then it can create a little bit, mixed states, then it can create a lot of trouble for LOCC. So first step is that let us consider for the pure states alone. And we know that the situations are there when the input and output states are pure states, but they cannot be distinguished by LOCC. Okay. So, so let us try to figure out what can be the, the rules, what can be the necessary conditions which we can write down for this, LOCC transformations. Okay. Now see, for LOCC, we already have a necessary condition just for one state. Okay. So if you have an input state chi and an output state eta, and they are pure states, pure bipartite states. So they can be written in the Smith form, and they have the Smith coefficients, which are alpha I and beta j's respectively. Then, and if you write them in the increasing order, then there is a measurization condition which determines that whether this chi can be transferred to eta. This happens if and only if this measurization inequality holds. That summation of I is equal to 1 to L alpha I square is less than equal to summation I is equal to 1 to L beta I square. So this is what is called as the Nelson criterion. So this condition must hold if I want to start, right? Because I want to have, let's say, n number of input pure states and n number of output pure states. For each pair of these input and output states, this condition should hold, right? So because we are considering LOCC for each pair, this psi1 to phi1, psi2 to phi2, for each pair, this should work out. So this condition must be true for every such situation. Okay, just a second. Yeah. This condition must be true for each pair of these things. Now, something more. Something more is the following. I have the input states S psi, let's call this as S psi as the set of all input states, and S phi is the set of all output states. Okay. Now I know if I take a probability distribution Pi, and let us make a state rho depending on this initial input state psi and the probability distribution P hat, which is like P1, P2, Pn, summation of Pi is equal to 1. That is this ensemble I from 1 to n, Pi psi, ket psi, bra psi I, and similarly we do for the output states also with the same probability distribution. Then what do we get? I get an input rho psi, and rho psi p, and an output state rho phi p. Okay, it's a p dependent, probability distribution dependent. But assume that if you have a transformation like this, LOCC transformation, then what can I say about it? That this object, the input state's entanglement, it's a bipartite set. So there is it can have an entanglement. So with respect to some probability, some entanglement measure, it can have some entanglement, and similarly the output states also have some entanglement. And now I know one thing very well, that under LOCC transformation the amount of entanglement should not increase. Okay, so let us call this this should also hold, that if there is an LOCC transformation, then the input states of entanglements and the output state, the output mixed states entanglement should be, input should be the greater than the output states entanglement. Okay, this must hold. And as you understand that this holds for every probability distribution T, whatever you can think of. Okay, so this is the second condition. The third condition is the very similar kind of a thing. Instead of the entanglement measure, I can ask the same question for the distinguishability measure, and the inputs distinguishability measure should be greater than the output states distinguishability measure. So let us do it once again. Condition A I call as the Nelson's criteria. That is, Nelson's criteria should hold for each pair. Condition B, for any probability distribution, you make an ensemble of inputs, make a single mixed state, and similarly with the same probability distribution, you make a output single state, and the transformation holds. Okay, that the amount of entanglement for the input state should not be should be more than the amount of entanglement for the output states, and similarly for the distinguishable with respect to the distinguishability measure also same thing holds. Let us call it as the point number C. Okay, now what I want to show is simply the following, that this is not all these three conditions, they are very reasonable. Okay, and this is I mean, it's a common sense to look at it, but they are not sufficient. Okay, and I cannot drop any of these conditions. I mean, like what I can, whenever I write a set of mathematical, things that you should condition A, condition B, condition C, condition D, I like to see that whether I can drop one of them and make my list a little shorter. Now I would show that this cannot be done. So first thing, okay, so it's not going. Yeah, first thing, holds B and C not. Okay, so consider these three sets. This Bell state 0 0 plus 1 1, and output will be the phi 1 would be 0 1 plus 1 0. Okay, and similarly this is again another Bell state, but output is a separable state. Then again this is another state, the separable state to another separable state. Okay, it is easy to check that the first condition is satisfied, because you see by Nelson's criteria, you can just put, you don't need to even look for the Nelson criteria. I mean, I can leave it as an exercise for the students who are here to find out a local unitary transformation which changes to psi 1 to phi 1. Okay, so try to find it out. It's not too difficult. Psi 2 to phi 2 is also very easy. You see, it's a pure states and to mixed states, so you can do that, and same thing goes for. So A is actually very straightforward. I am not. It's not too difficult. Now, what's about B? B is, recall, B is with respect to a probability distribution. Any probability distribution, their ensemble of these three states, whatever the mixed state you get, its entanglement should be greater than the with respect to the same probability distribution ensemble of the output states. Okay, so you take a P which is between 0 to half, and you take the probability distribution with this corresponding to that P. So P1 minus 2P. Okay. Then you see, you can check that for all P between 0 to half, this rho of sigma, rho of psi comma P is separable. However, okay, that is not too difficult to actually check, because you see, after all, we are doing it for the 2-qubit system. So you can take a partial transpose and work it out that this is not, but this is not actually, I mean, it's easy to entangled, but the input state, so mixed state is not entangled. So you cannot have an LOCC transformation such that the mixture, the output becomes entangled, but the input is not entangled. Okay. So that doesn't work out. Now, the why the distinguishability measure it doesn't work out is a little bit more subtle, and that is actually, I don't want to go the full argument, but this is a very, very famous work of Walgett and Hardy, and you can have a look at that thing. They came up with the same example and they showed that this doesn't work out. Okay. Some more. Let's give some more, but I would not give all the cases, but let's have some more things. That let's say the B satisfies, A and C do not satisfy. Second, I take a set of input states like this and a set of output states like this. Okay. So what it is? Okay. Maybe I should, maybe before I coming to that, I should tell the Walgett and Hardy's thing, because I may use it also later. So the theorem what they came up was the following, that if you consider 3 orthogonal 2-qubit pure states, then they can be distinguished by LOCC if and only if at least 2 of the states are the product states. Okay. So that actually shows that this thing doesn't work out, and this set is kind of more distinguishable and this set is less distinguishable, and hence obviously there's such a transformation actually increases it doesn't increase the distinguishability. LOCC transformation does not increase the distinguishability, so this is not possible. So this is the idea for the point number C. Okay, let's come to the item number B, the situation in which you have more, what I should say, the entanglement criteria holds, that is the item that B condition holds, but the other 2 conditions do not hold. Okay. Now, take this set of input states and take this set of output states. Okay. So B is satisfied. So you consider any probability distribution. Okay. This is you understand that I am taking that not only the qubit system, slightly higher dimensions actually. And if you so in a slightly higher dimension, it's a dimension 4 actually, and your basis is 0, 1, 2, 3. And then you can actually see, if you consider the measure of entanglement as entanglement of formation, then you can show that your with respect to the probability distribution P1, P2, P3, and P4, where summation of Pi is equal to 1, then clearly the equal mixture of both these 2 output states, that is half probability actually. Then you see clearly that the half of ket psi 1 psi 1 plus half of ket psi 2 psi 2 psi 2, this is a separable state. Whereas if you do the same thing for the output states, then there are then it is an entangled state. So some of these things comes pretty nicely, but one has to carefully, what we had to do was that carefully find out all the examples. Okay. Same thing holds for this kind of situation where the calculations can be a little more difficult, that B and C are satisfied, that is the entanglement measure is satisfied, the distinguishability measures issue is also satisfied, but Nelson's criteria is not satisfied. So I don't want to go in that thing. Let me try to wrap up the situations. Of course, there is a very obvious situation when the case A, B, and C are all satisfied. There is nothing much to do. You pick up any set of input states, psi1, psi2, psi and you take a local unitary operation, U tensor V, and whatever you apply it upon all each of these psi i's, and whatever you get it, you call it as a phi I. Naturally, it will satisfy your measure, your Nelson's criteria. It will satisfy your entanglement inequality, or it will satisfy your distinguishability measure, everything. Okay, so this is the most obvious case where the A, B, and C all are satisfied. Okay, so let me summarize what exactly I have done here. That is, we have worked out that this kind of a situation, okay, that SA is the set of all possibilities that the condition A is satisfied. SB is the set of all situations in which the condition B is not satisfied. SC is the case where the condition C is satisfied. Then you see, we have found out, actually, you can check the full paper, but I don't want to give all the situations, that anything which is there in this part, which does not, where C is not satisfied, B is not satisfied, this portion is non-empty. The case where B is satisfied, A and C are not satisfied, there is an example. The case when C is satisfied, A and B are not satisfied, there is also an example. Where the situation when A and B are simultaneously satisfied, that is their intersection, but C is not satisfied, it is there. Similarly, A and C are satisfied. So SA intersection SC means that A and C conditions are satisfied, B is not satisfied, there is an example. And B and C are satisfied, A is not satisfied, there is an example. Of course, A and B and C, all three satisfies, there is an example. Of course, that, as you can already see, that is my last one. So we have found out that by using this Venn diagram kind of thing, that I cannot drop any condition A, B, and C from the list. Okay, so they must, all three should be there in the case. Okay, now I can ask the most natural question, that are they sufficient? Like, I'm a mathematician, so I would like to know that whether this is a sufficient conditions also. And unfortunately, the answer is no, they are not sufficient. So let me give a proof outline of it. So these are these necessary conditions are not sufficient. So let us consider this input and output states, again something which we just now have seen. Then that's why I came to that point, that these two Bell states, 0 0 plus 1 1 and 0 0 minus 1 1, and output states are alpha 0 0 plus beta 1 1 and beta 0 0 minus alpha 1 1, where alpha is greater than beta is greater than 0 and alpha square plus beta square is equal to 1. I am taking the real numbers, nothing complex. So now, does it satisfy all the things? Okay, the Nelson's criteria is satisfied for each pair. So A is satisfied. Now, to show B, you see the density operators, if you consider with some probability measures, then you can find out you can consider the concurrence as one of the measure of entanglement. And you can see that the condition B is also satisfied by using this measure of entanglement. And condition C, you see both these two sets are distinguishable locally or globally. Okay, so the condition C is also by and large are satisfied. Now, what I want to show is that I want to show that there is no LOCC transformation possible between this such that this input state will go to this output state, and this input state psi 2 will go to this output state phi 2. Mind it, again you recall, this is not, this is a single LO. I am looking for a single LOCC transformation. Okay. Now I use a small trick here. The trick is the following, that, I know that the set of all LOCC transformations are actually sitting inside the set of all separable transformations. So if I can't do it by using the LOCC, the separable, it is sitting as property. Okay. So if I cannot do it by using separable transformations, then I can't do it by LOCC transformations also. So let's use that. So let us have this set of separable transformations. S is equal to AK, BK, where AK and BKs are, Krauss operators satisfying this equality that, that it's a channel equality, that A star, A dagger, AK dagger, AK, tensor BK dagger, BK is equal to identity. Okay. It's a separable operation. So what will happen is that this S of psi I will be something like summation K, AK tensor BK psi I, AK dagger tensor BK dagger. Sure. So the psi I have used a little bit loosely, which means actually the ket psi I, bra psi I. I think you understand that the projections. Okay. Now, what I want, this psi 1 will be the phi 1 and psi 2 will be the phi. Okay. So what we will have practically, I would have the following, that AK tensor BK psi 1 should be something like mu K1 phi 1, and AK tensor BK psi 2 should be something like mu K2 phi 2. Okay, where mu K1 and mu K2 are complex numbers. Okay, now for given K, I need to consider two possibilities. One, that mu K1 and mu K2 are both non-zero, or the second possibility that one of them is 0. Now, you consider the case where both this mu K1, mu K2 are non-zero. You put the psi values, actually psi 1 and psi 2, they are the vectors, and then you are taking the projections. So if if you put it and then you do a little bit of simplification, then you eventually find out equality like this, that AK tensor BK acting upon 0, 0 should have something like a equality like this. Okay. Now, now for this 0, 0, you see 0, 0 is a separable state. So I can make it like, ket 0, 0, bra 0, 0. So that side also AK tensor BK. So the left hand side will be eventually a separable state, whereas the right hand side, okay, the right hand side must also be a separable state, because you are after all doing a separable transformation. So the separable state must go to a separable state. So the right hand side has to go to a separable state, and there are the possibilities are that this ratio, the moment you apply the separability criteria, you can do it, because here it is you are doing the qubit system. Then you see that after cancelling everything, you get mu of K1 by mu K2 will be either minus beta by alpha or
Ritabrata,
alpha by beta.
please try
Yeah,
to wind up in 5 minutes, please.
it will be over. Just
Okay,
just give me
please.
2-3 minutes. It will be
Yeah,
over.
sure.
I'm almost done. Now you see, for the other case, see, I did it for the 0, 0. And similarly, I will get another equality for 1, 1. That is also separable. So the right hand side should also be a separable quantity. And that is a separable quantity. When it is easy to check by using the partial transpose. So you get, after all these things, you get this mu K1 by mu K2 will be again, now here comes the problem. It is either beta by alpha or minus alpha by beta. But you see, for the first one to hold, actually, that AK tensor BK or 0, 0, if you consider the first case that it is this ratio is minus beta by alpha, then from the second equation you get it is actually alpha by beta. and vice versa. Okay, so you are getting a contradiction on this ratio, because the first one will give you one ratio, but if you put but the second one will give you the other ratio. Actually, both together cannot hold. So this is not possible. So there is no other possibility is there that one of them is 0, the other one is non-zero. Okay, now let us assume that mu k2 is 0, mu k1 is non-zero. Okay, now you would see that again you put it and you do the calculations and you do a little bit of simplification. You find out that AK tensor BK psi 1 will be equal to mu k1 of phi 1, and AK tensor BK psi 2 will be equal to 0. The left, so if you do this adding and simplification a bit, then you would see that the left hand side will be a bit product state and the right hand side will become an entangled state with all these things. That psi 1 and psi 2, if you add it, then the left hand side is a product state, right hand side is an entangled state. That cannot be possible. That means in a sense that there is no separable transformation which transfers the left hand side to the right hand side. This inputs to these two input states to these two output states. So it is very interesting that these three states and these three conditions, which are very, very common sense, tells that this should hold. I can't drop any of them, and they all are, they are all necessary, but they are not sufficient. So there are a lot of things to work on this thing. What I have not seen is, of course, that all the calculations and all the examples which you painstakingly managed to find out. And also we show that, also I have not shown that where exactly is the position of this set transformation problem. We know that it is, the LOCC is strictly sitting inside the set of all separable set of all separable transformations, and we have shown that thing that this cannot be done by the set of all separable transformations in that hierarchy. So it cannot be done by the LOCC transformations also. So there are some more interesting things about it in that hierarchy, but I don't want to go in that in detail right now. So thank you all. Thank you, Shubhashish, also. And I should thank Prasant Panigrahi also. So of course, DST is now sponsoring all of us. So that is also there for it. So thank you all. Thanks for your attention.
Thank you, Ritabrata. Now we have time for questions. Please feel free to ask.
Okay, so if you want, you can also ask me personally by email. Actually,
Yes, 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 yes.
yeah. So mine can be find out rb@IISER BPR, or you can go to IISER BPR Maths Department and then find it out.
So if I may ask a question, I don't know, it would be a very naive
Yeah.
question, but suppose one is interested in particularly in open quantum systems. So in particular, I have some say a specific non-Markovian channel in my mind. Then how will this how will your setup help in will it help in characterizing which channel would be useful or most efficient in these transformations, or am I asking a wrong question, basically?
No, you are actually starting with a research problem direction, actually. So one, for the LOCC conversions, it doesn't really help at all. Okay, because in LOCC, we know so little that if you ask me for the Markovian and etc., probably even see all these calculations, I couldn't do it for the mixed states.
Yes,
Right.
yes, yes, yes.
So because LOCC community works on pure states only so far.
Okay, okay,
Right.
okay.
So this is one thing. The second question is that what you are asking is actually pretty important. Uh, but here for the probably you are asking about the dynamical maps, which it is so called
Yes,
the
yes,
dynamic.
yes,
Yeah. So how
yes.
you can do that, whether there is a possibility a dynamical map or not. So
Ah,
The idea is that there is a work by Francisco Buscemi and Nilanjana Datta. I think it came in 2012 or something like that, PRA. I don't think it was a PRL, but it was in PRA. And they tried to do something similar in that direction.
Okay.
But it was still a bit half-baked, actually. So it is not, they didn't really go fully to the dynamical maps, but they use some of the characterizations on that direction.
Okay.
Yeah, but I think there is a possibility that one can take that paper and make it as a dynamical map version of it.
Okay, that's great. One can, maybe we can talk about it more.
Yeah,
later.
yeah, sure.
So if
Sir, I have
so,
a
please
question.
you are
Somebody said
feel
something.
free to contact Ritabrata with
Yeah, somebody I think
with the
said
name.
he has a
Yes,
question.
Sir, I have a
somebody has
question.
a question. Yes, please feel. Go ahead. We have time.
Sir, maybe it's a small question, a small doubt for me. What are these local operations and classical communications like between Alice and Bob? Something.
Yeah.
What exactly? What kind of operations I can say these come under LOCC and what not?
Anything, whatever you can do locally, and then whatever you can do, like you can do your local unitary transformations locally. The Alice and Bob in their labs can do a transformation. They can do measurement. They can get measurement outcome. They can share it between them. I mean, they're all standard LOCC transformations.
Okay.
Okay,
So,
we are assuming everything, whatever is under the sun, whatever is possible under LOCC, we are considering everything.
okay.
Probably you can ask the question that what may happen for one way, two way, etc., LOCC and all that. So at the present we are in two way, though we have not explicitly said that, but see, we use several of these, the results by several other people for the distinguishability measures and things. So these are all two-way LOCC. So one can ask the question about if you can consider only one-way LOCC, then whatever works out, and more restricted classes. But you see, we still don't have an idea about LOCC properly. Mathematically, it's not there is no good definition. So there is a lot of thing to do. I mean, we are doing this work. We are continuing this work also.
Okay.
This is probably the first paper in this direction in this way type of things. Yeah.
Thank you, sir.
Yeah. Anybody else?
Okay. Thank you, Ritabrata, once again.
Thank you. Thank you for calling also, and give my regards to Professor Prasant Panigrahi for organizing this thing and calling me. Okay. So bye.
Thank you. Bye.
Well, I will be online, of course, for that.
Yes. So, Tomek is the next speaker. Hello. Hi, Tomek.
Can you hear me?
Yes, I can hear you. Very nice to see you.
Likewise, in a sense. Very nice to see you.
I have to get my video off, otherwise my the broadband is not too good here. So, Tomek, I've known Tomek for quite some time, and he's a very interesting person. And interestingly, he's not only into quantum information deeply, but he's also taken it into interfaces with biology and things like that, which is quite a novel thing. And today, he will talk about a thing he has been working on for quite some time, and this is this mediated dynamics, which is very interesting, and I hope it would be of interest to the audience also. So, Tomek, please go ahead.
Thank you very much. Many thanks, Subhashish. And so let me start with formally thanking the organizers. So many thanks to everyone involved in this. I'm really happy to be able, thank you for this kind invitation. I'm happy to say a few words about this mediated dynamics. And I'm really also very honored because I believe this is probably a historic event, must be one of the longest quantum info conferences in history. So the only thing that I really regret is that I cannot see your faces.